All right, good afternoon, class. This is what are we up to? Lesson 22, section 5.3. This is covering our last and final section for this class. So we're almost done. This is going to be the culmination section, which really pulls everything together we've learned in this class. Eigenvectors, eigenvalues are going to be a big day today. This idea of matrices being similar, they're going to be super important for prediction modeling, which we're going to talk about. Um, Linear independence, vertical matrix theorem, determinants, so on and so forth. All the stuff we're going to be using to complete this final section of this class. So first, I do want to briefly talk about prediction modeling and what matrices could possibly have to do with that, right? Well, for example, oftentimes this is done for population modeling. You can imagine, for example, that you could have a population of deer and maybe a population of wolves in some national park, right? So this vector can be represented as a column vector where we're going to say the first entry is how my deer population is doing. And the second number is going to be how my wolf population is doing, right? Well, then maybe via experimentation and whatnot, well, let me write it this way. And maybe via experimentation and collecting data, we're able to create some kind of model which can tell us, okay, how are these populations going to change in 1 month? Is the deer population going to crash too much? Are the predators, the wolves, possibly eating too much of the prey, killing too much of the prey? Is the wolf population too large? Is the population too small? This can tell us what is the population going to be after some amount of time. Assuming this is an accurate model, maybe this predicts by the month. Maybe even depending on how accurate the model is, maybe this can even predict by the week or something, right? So this is going to give some new output, which is going to be some new population prediction. Depending on how good this prediction is, that's how accurate this answer is going to be, right? Or this output. Okay. But what if instead I say something along the lines of, okay, well, that's all fine and good, but I want to use this model to predict what is going to be the output after, oh, I don't know, let's say, you know, 300 months or something, right? You're trying to predict far out into the future. If this is like a national park or something, you want to predict far enough into the future so you can tell, like, hey, if something bad is going to happen, or if the populations are going to be at bad levels in 4 or 5 years, then you have to know now in order to start like planning for that, preparing for that, so on and so forth, right? Now, of course, these models don't just have to be for population models. This is just an example that I'm showing you guys, all right? But the issue then is like, well, if you want to predict what's happening like 300 months from now, that means you would have to multiply this matrix 300 times. You have to take A times this, and then A times that, and then A times that, A times that, A times that, A times that, so on and so forth. You would have to do 300 calculations with this matrix. Now, okay, sure, you could write a program to do that, and that possibly wouldn't be so bad. And for this example, this is just a 2 by 2, so okay, that's doable. But if this were a more complicated prediction model, what if A, for example, was a 20 by 20? If you have 20 different species you're trying to calculate for, living in some area, in some kind of ecosystem, maybe you have 20, 25 variables you're trying to account for, in which case, trying to multiply a matrix that's a 25 by 25 300 times, well, even then, there comes a point where even for a computer, that calculation can start to take a while, right? Now, sure, that can be done, and if you're patient, yeah, that'll work, right? But part of the point here is that we would like to find a linear algebra solution where this kind of calculation is much quicker and easier to do. That's the point of today's lecture. That's the point of what we're going to do in 5.3. Why we care about this is that we want a quicker, faster way to make these kind of calculations. All right, well, how are we going to do this? Well, recall, I think this was back in maybe chapter 2 or chapter 3. We mentioned the definition for a diagonal matrix, right? So what does that mean? So recall, a square n by n matrix is called diagonal. What does that mean? If only the diagonal entries contain non-zeros. Right? In other words, anywhere that is not the diagonal must be 0. The only place you can have not 0 is on the diagonal. Now, that does not mean the diagonal has to have non-zero entries. It just means that's the only place you can have non-zero entries, right? So the zero matrix, for example, is diagonal. The identity matrix is also diagonal. The point of being a diagonal matrix is that your non-diagonal entries must be 0. What's happening on your diagonal? Well, whatever you want, right? But so long as your entries that are not on the diagonal are 0, it is a diagonal matrix. Okay, fine. But why do we care? How does this help us? What's special about diagonal matrices? Well, now let's consider an example. I'm going to say D, the matrix D, so D for diagonal, is going to equal the matrix 5, 0, 0, 3. All right. Now, like before, we discussed, like, part of our motivation for today is we want to think about what does it mean to raise a matrix to a really high power, right? I want to multiply it like 300 times or 1,000,000 times or something. Depending on how like accurate your model is, like if your model predicts by the hour, but you want to know what's happening in 3 weeks, well, then that's 24 times per day times another 21, right? Or if you're trying to predict for a year from now, but your model predicts by the hour, you got to multiply that matrix a bunch of times. So, but what happens when we raise a diagonal matrix to a power? Well, let's just play with D squared and see what happens. So this is the matrix D times the matrix D. And what happens? Well, when I do my dot product, I'm going to have 5 times 5 is going to be 5 squared plus 0. And then 0, 0, 3 squared. Well, that's interesting. For this diagonal matrix, it turns out when I raise it to a power, it's the same thing as raising the diagonal entries to that power, right? So in other words, what's really nice and special about a diagonal matrix is that a diagonal matrix raised to any power is just the same thing as raising the diagonal entries to that power. So if you're trying to calculate, okay, what is this matrix raised to the 600,000 power? Well, you can just raise these numbers to the 600,000 power. Now, sure, raising a real number to a really high power, sometimes that can take a little bit. But that's going to be much faster than if we were trying to multiply this matrix with the dot product over and over again 100,000 times, right? So this is still going to be computationally faster and computationally better, more efficient for any kind of computer program trying to do this kind of thing, right? Okay, great. But what if the matrix isn't a diagonal matrix? Then what do? Is there some way to rewrite it as a diagonal matrix to make our lives easier? That's what we want to talk about next. What do we do if the matrix is not diagonal? Well, in part, this is where that definition for similar matrices in last lecture is going to come into key play. How do I mean? Well, let's do the example first. Excuse me. All right. Suppose A equals the matrix, equals the matrix 7, 2, -4, 1. And I would like to know what is A raised to the 604,800, right? Some big number where even if you were doing this on your calculator, that's going to take forever to do, right? So it's like, okay, how can we do this instead? This matrix is not diagonal, but if I could somehow rewrite it as a diagonal matrix, maybe that would be helpful. Okay, well, I'm going to go ahead and give you the solution here, and then we're going to do examples later about how to find this solution. But remember our definition for similar. Instead, notice A is similar to the matrix D, 5, 0, 0, 3. This is the same matrix D we had just a moment ago when P equals 1, -1, 1, -2. In other words, what does it mean that they are similar? This means A equals P D P inverse, right? So what we have here is that, okay, A itself might not be a diagonal matrix, but it is equal to this product, which has a diagonal matrix in the middle of its product. Okay, and right, this is our definition for similar matrices given in the 5.2 lecture. Okay, fine. But why does this help? How does this help us solve anything? Well, think about this. If we raise it to a power, A squared means I have P D P inverse times P D P inverse. But lo and behold, what's special? What happens? Well, the P inverse and the P in the middle are going to cancel each other out. They're going to become the identity. I'm going to have P D identity D P inverse. But D times the identity is just D. So really what I have is D times D in the middle. In other words, I have A squared is now equal to P times D squared times P inverse. Oh, that inverse is a little off the side here. Let me fix that. How's that? A little better. Okay. So how does this help now? Well, now, instead of raising the matrix A to a power, it's really just the same thing as raising this diagonal matrix to a power. But as we just saw, raising diagonal matrices to a power is really easy to do. In fact, we can check, well, what about A to the third power? Well, this is P D P inverse, P D P inverse, P D P inverse. But again, what happens? P inverse and P will become the identity. P inverse and P will become the identity. What am I left with in the middle? D times D times D. I have P D raised to the third P inverse. So now A to any power, even A to the 604,800 power, is the same thing as P times D raised to that power times P inverse, right? So the only calculation I have to do is raising d to a power. But because d is diagonal, that's the same thing as just raising the diagonal entries to that power. So this is an easy calculation, and a computer can do this very quickly, or at least much quicker than the alternative of raising the original matrix A to that power and doing the dot product 600,000 times. All right? So that's all fine and good. We see what's special here. But if I just tell you the matrix A and I don't tell you D and P, how do we find D and P? How do we know what A is similar to so that we can rewrite it as a product with a diagonal matrix like this? Well, this is where the diagonalization theorem comes into play. Oh, and in fact, I'm also going to say, anytime you can rewrite a matrix as this kind of product, A is called diagonizable. So let me go ahead and give that definition. We'll do that down here. Definition: A is diagonalizable. Let me make sure that's still on the screen. Okay, good. A is diagonizable if and only if and only if A can be rewritten as the product of this, where D is diagonal. Diagonal. So if a diagonal matrix in the middle like this, why do we like this? Well, when the matrix is diagonizable, that means raising it to a high power is a simple and easy calculation. If the matrix A is not diagonizable, well, then our only option is to do the dot product 600,000 times, which sucks, but that does happen sometimes. Okay? All right, so how do we know when a matrix is diagonizable or not? I gave you an example where it is diagonizable, but how do we tell? This is where the diagonalization theorem comes into play. And this is kind of the last big theorem we're going to talk about and use in this class. All right. The diagonalization theorem. All right, what is this? Well, an n by n matrix. So first of all, we're talking about square matrices. If it's not square, it's not diagonizable. An n by n matrix A is diagonalizable if and only if we have A has n linearly independent eigenvectors. So the start of chapter 5, chapter 5.1, we talk about eigenvectors and eigenvalues. What's really happening here? The fact that I have n linearly independent eigenvectors and that I have an n by n matrix, right? That means these column vectors are inside of Rn. But if I have n linearly independent eigenvectors, that means I have enough eigenvectors to span the space Rn, right? In fact, A equals PDP inverse. This is its diagonalization with D diagonal precisely when the columns of P are n linearly independent eigenvectors from the matrix A. Right? So in fact, this tells us how we construct the matrix P. The matrix P is going to be made out of the eigenvectors. And when we have n of them, it will form a basis for Rn. All right? But why is this true? This seems kind of like out of the blue. Why are eigenvectors so special here? Okay. Well, let's think about the why behind this proof. Suppose the matrix A is diagonalizable. All right? This means A equals PD P inverse for some matrix D, right? For some diagonal D. Okay, fine. Now, if I multiply both sides by P, if I multiply on the right side by P, then we have A times P equals P times D. Okay, fine. Now, what is this matrix P, and what is this matrix D? Well, my matrix D is a diagonal matrix. It has some constants. Maybe I don't know what those constants are, but I'm going to call them lambda 1 and lambda 2 for now. There's a reason for that. In fact, the diagonal matrix is going to be made out of eigenvalues, but we'll see that in just a moment. Okay? So AP equals P times D, where P just has some column vectors. Right? These are column vectors. Okay? But now what's happening here? Well, when you do the dot product with A times P, this is A times these column vectors. So we have on the left side, A times V1, A times V2, and this is supposed to equal, we do the dot product with the matrix P times this matrix D. On the left side, we get lambda 1 V1, lambda 2 V2. But P is invertible according to this formula, right? A equals PDP inverse. P is invertible, which implies P is linearly independent, which implies V1 and V2 are not 0, right? They can't be 0 vectors if P is linearly independent. Okay. But if V1 and V2 are not 0 vectors, look what happens. A times V1 equals lambda 1 V1. A V2 equals lambda 2 V2. In other words, V1 is an eigenvector because A times V1 is actually just a multiple of V1. So the very structure of this equation, when A equals PDP inverse, implies that you have eigenvectors here. In fact, your matrix P is made out of eigenvectors. But these are linearly independent, and I have 2 of them. And this is an example drawing I just made up. This was a 2x2. So I have 2 linearly independent eigenvectors, which is exactly what the theorem says I should have, right? So this is the breakdown, and this tells me exactly how I'm going to construct P, how I'm going to find D. D is a diagonal matrix with my eigenvalues, and P, so here you want to pay attention, the order matters. The order is key here. Notice V1 was an eigenvector with lambda 1. v2 is an eigenvector with v2. In other words, whatever order you put your eigenvalues in, that's the same order your eigenvectors need to be put in. So if you put some eigenvalue in the first column, its corresponding eigenvector needs to also go in the first column in order to make this happen, right? In order to make both sides of this equal, this must happen, okay? So, all right, let's look at some examples. Let's see an example for how do we actually do this? How do we actually find diagonalization? And the key here is that it's going to come down to vectors and seeing, do we have enough eigenvectors or not? We need n linearly independent ones, okay? All right. So here's an example. Let's say a equals 1, 0, 6, -1 is a diagonalizable. All right, this is the question we would like to answer. Well, we're trying to tell, is there a way for A to equal PDP inverse? Is this possible? Well, to make that possible, we need a matrix D and we need a matrix P. P is made out of eigenvectors and D is made out of eigenvalues. So step one for this problem is always to find eigenvalues. Find eigenvalues. All right. How do we find eigenvalues? We can use the characteristic equation. Determinant of A minus lambda I, and we want to set it equal to 0. Okay. Well, A minus lambda I, I'm subtracting lambda from the diagonal. Luckily, this is a 2 by 2, so when I take its determinant, I'm going to have 1 minus lambda times -1 minus lambda minus 0. So this is it. This is my characteristic equation. When does this equal 0? Lucky for us, it's already factored. Lambda 1 equals 1, or lambda 2 equals -1. So we have two eigenvalues. This is good so far. In fact, this is already enough to stop and say the matrix A is diagonalizable. Why is this enough? According to the diagonalization theorem, I need n linearly independent eigenvectors. So why is this enough? Well, I have two different eigenvalues. Now remember when we talked about eigenvalues, to be an eigenvalue means that you have a non-zero eigenvector, at least one, associated with it. But that means I have at least some eigenvector, non-zero eigenvector, associated with both of these eigenvalues. But because they come from different eigenvalues, right? I have two distinct eigenvalues. Remember that when we have eigenvectors from different eigenvalues, they're automatically linearly independent. So having two distinct eigenvalues implies two linearly independent eigenvectors. So even though I haven't found the eigenvectors, based on those theorems we discussed in 5.2 for the characteristic equation, or maybe it was 5.1, this is already enough to tell us we have enough linearly independent eigenvectors, therefore it's diagonalizable. Okay, that's fine. But what if the question says find P and D, right? I want to find the matrices that make it diagonalizable. All right. Well, from step 1, we've already found D. D is a diagonal matrix with our eigenvalues. So we have 1, -1, 0, 0. So great, we found our matrix D. All that's left then is to find the matrix P. How do we find P? I need to find the eigenvectors. So step 2 now is to find a basis for each eigenspace. Remember, the eigenspace was a span of vectors, a span of eigenvectors that correspond with each eigenvalue. If I can find the eigenspace which goes with lambda 1, that's going to tell me what my eigenvectors are that go with lambda 1. Okay. But how do I find the eigenspace? Well, I need to find the eigenvectors, right? I need to figure out for what x does a times x equal lambda 1 times x. Well, if I try to solve for x here, we've done this before. This is ax minus lambda 1x. I can factor out the x. In other words, I'm trying to find the solution to this homogeneous system set equal to 0. Well, when lambda 1 is 1, this is just a minus the identity. So I'll have 0, 0, 6, -1, augmented with 0. Now, lucky for us, this is already in echelon form. I can swap row 1 and row 2 if I like, but we can already tell by looking at this, I'm only going to have this one pivot, right? x2 is free. x2 is free. So what's x1? 6x1 minus x2 equals 0. 6x1 equals x2. x1 equals 1 over 6 x2. So what is my vector x? Well, x1 equals 1/6 x2, and x2 equals x2 because it's free. But I can pull out the x2. So x equals any multiple of 1/6 and 1. In other words, my eigenspace, which corresponds with lambda 1, equals the span of 1/6, 1. I think I'm running off the screen. I am. So let me write it down here. The eigenspace corresponding with lambda 1, maybe I can write it smaller, is the span of this vector, 1/6, 1. That's better. Okay. So this is telling me what eigenvector goes with lambda 1, which means this is telling me what I should put in the first column of P. All right. So we're going to make a little bit of space. Since we already finished step 1 here, I'm going to erase step 1. All right. Right, okay. So we're trying to construct the matrix P. P has to be made up of eigenvectors, where each column is an eigenvector, which goes with the matching eigenvalue I have in that column. So V1 has to be an eigenvector with lambda 1. Okay? Well, I already know all the eigenvectors with lambda 1 is any multiple of this vector, right? Now, what you could do, and this is perfectly correct, if you do this, I would give it full credit on the final exam. If you just wrote for the first column 1/6, 1, that's perfectly fine. That's an eigenvector. That would be a correct answer. However, what I would suggest instead is, well, if the eigenvectors can be any multiple, right? The set of eigenvectors, this is a space, this is a subspace of R2, it's any multiple of this vector. So if I multiply it by 6, so I don't have a fraction, I get 1/6. This is a multiple of this vector. So it's in the space. It's an eigenvector with lambda 1. And now I don't have any fractions. This answer kind of looks nicer. Okay, so we're almost done. All that's left is I need to find the eigenvectors. I need to find the eigenspace with lambda 2. Well, rinse and repeat. Do the same process, right? We need to find the solution to the homogeneous system with lambda 2. So now, look over here, lambda 2 was -1. So I'm adding the identity matrix. So I have 2, 0, 6, 0. Okay? So this is now the homogeneous system we're trying to solve. And lucky for us, we can see pretty easy with the row reduction. If I multiply row 1 by 3 and subtract it from row 2, then we're going to get this echelon form. All right. Again, x2 is free. And so what is x1? Well, 2 times x1 equals 0. So when I solve for x1 equals 0. So my vector x here equals 0, x2. So when I factor out the x2, I get x2 times 0, 1. In other words, my second eigenspace, I'll erase what we did over here. My second eigenspace is the span of 0, 1. Well, lucky for us, this is already a nice vector. There's no fractions. So this will become my second column. And lo and behold, we're done. Okay, great. We found our matrix P. We found the matrix D, and that's it. Now you'll see from this formula, this is A equals P times D times P inverse. Yeah, you could go ahead and find P inverse by taking the inverse of this matrix. Oftentimes, a lot of these problems, they're not going to ask you to find P inverse. Since this is chapter 5, this is well after inverse matrices we did in chapter 2. It's kind of assumed that you already know how to find P inverse, right? So a lot of the questions you see in the textbook, they're just going to say, what is the matrix P? What is the matrix D that makes A diagonizable if it's diagonizable at all? All right. Now, the other key feature I want to highlight here before we do one final example is also notice here and recall the number of free variables. Those are the number of variables that are going to appear in your answer for your vector x, right? The free variables is the number of variables that's going to appear in your vector x. So the number of free variables, when you pull it apart in a parametric vector form, that's why it was so important that we learned that format. When we pull it apart in parametric vector form, the number of free variables is going to tell you the number of vectors you have in your span. So sometimes looking at your number of free variables can tell you right away whether you're going to have enough vectors or not. Okay? So let's check this out. And part of the reason for this is, why is this happening? The number of free variables is telling us how many vectors we get in the parametric vector form. In other words, the dimension of any eigenspace is equal to the nullity of, and I might be running out of space. Oh, we're okay. A minus lambda I, right? What is the nullity of A minus lambda I? Well, that's the dimension of the null space of A minus lambda I. That's the number of free variables for the matrix A minus lambda I. So all that dimension stuff we talked about in chapter 4, that can help us solve some of these problems. If you don't have enough free variables to have a large enough dimension to have enough vectors in your span, then you might not have enough eigenvectors to be diagonizable. In fact, that's what exactly happens in this second example. So this first example we did, this was an example that was diagonizable. But what about an example where it's not diagonizable? All right. Well, now let's suppose our matrix A is the matrix 2, 4, 3, -4, -6, -3, 3, 3, 1. All right. Well, step 1, we need eigenvalues, right? So step 1, we need eigenvalues. We need to solve the characteristic equation, right? Set this determinant equal to 0. Now, for the sake of time, we're just going to kind of go through this quickly. If you take A minus lambda I and then take its determinant, careful with the 3 by 3 matrix, it does get a little bit messy. This is going to equal negative lambda cubed minus 3 lambda squared plus 4. We want to set this equal to 0. Now, unfortunately, this is not a quadratic. This is now a third-degree polynomial. So we don't have a quadratic formula that we can use here, but we can factor it. Now, again, just for the sake of time, I'm going to skip over the factoring. If you've taken like pre-calculus or college algebra, you would have learned how you can factor this by finding the roots. Find a place where this equals 0. Sometimes that helps by graphing this. You can find where it crosses the x-axis, and then you can find where the roots are and use that to further simplify this and factor this. All right. So that's a prerequisite kind of piece of knowledge here for how to factor this. So I'm not going to go into too much detail here, but we get lambda plus 2 squared here. Now, what's interesting is that this was a 3 by 3. Now, before in the last problem, because I had 2 distinct eigenvalues. Now, here I have only 2. Does that mean it's not diagonizable? Well, not necessarily. Why? Well, lambda equal to -2, has a multiplicity equal to 2. Right? So what this means is that the dimension of its eigenspace, well, it's less than or equal to the multiplicity, right? So depending on what happens when we try to solve the homogeneous system for the eigenvectors, I might still get 2 vectors here. I might get 2 eigenvectors for this lambda. If I do get 2 eigenvectors for this lambda, then that means I have 3 and we're golden. But I don't know until I try to find those eigenvectors. All right. So, okay, next we need to go to step 2, find the eigenvectors. So step 2, we're looking at A minus lambda I, this homogeneous system, and we want to solve for x. So let's start with lambda 1 equals 1. I'm subtracting 1 from the diagonal. So we have 1, 4, 3, negative 4, negative 7, negative 3, 3, 3, 0, augmented with 0. Okay. Now, for the sake of time, I'm just going to go ahead and write in the row-reduced echelon form here. And we're going to get 1, 0, negative 1, 0, 0, 1, 1, 0, 0, 0, 0, 0. Okay. We get one free variable, which is kind of what we already expected, since we know there's at least one eigenvector that goes with this eigenvalue, and it has multiplicity 1, so we expect there to only be 1. All right? Well, we can solve for it. So what's x2? x2 equals negative x3 if I subtract this over. And x1 equals positive x3. Again, if I add this x3 over. So my vector x equals x3, negative x3, x3. Factor out the x3 and we get 1, negative 1, 1. So my first eigenspace is the span of 1, negative 1, 1. So we have one eigenvector so far. Okay, that's fine. Now rinse and repeat. Let's do the same process, but now for the second eigenvalue. Lambda 2 equals negative 2. So now I'm going to add 2 down the diagonal, so I have a double negative. So I'm going to have 4, 4, 3, negative 4, negative 4, negative 3, 3, 3, 3. Did I do that right? Yeah. Okay. Now again, for the sake of time, I'm just going to write in the row-reduced echelon form. We have here 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Now look what happened. I only have one free variable. This tells me right away that the dimension of my second eigenspace is equal to 1. In other words, I only get one eigenvector, one linearly independent eigenvector from the first eigenvalue, and I only get one linearly independent eigenvector in the span of this guy. That means I only have 2 eigenvectors, but that's not enough. I need 3 to be diagonizable, right? So therefore, A is not diagonalizable. All right. So that's not going to help us here. We can't do anything more. In other words, to be diagonizable, the dimension of your eigenspace must equal its multiplicity. In this case, that didn't happen. We only get one eigenvalue, or we only get one eigenvector. And in fact, if you look at the lecture notes on Canvas, I do have more detailed step-by-steps for finding the second eigenspace. And you're going to see it's the span of only a single vector. So we don't have enough eigenvectors. This is not diagonizable. All right. Very last thing, let's look at today's participation question. This is participation day 21, I believe. Okay. Participation day 21. Let me share my screen here. All right, looks like we're sharing. Participation day 21. Let A be a 4x4 matrix. So right off the bat, because we're talking about diagonalization, we need 4 linearly independent eigenvectors. Okay, fine. And we're told there are 3 eigenvalues. So we have an eigenvalue. I'm just writing these details on the board, and then we'll look at the board in just a moment. So we have 3 eigenvalues. Okay. Well, that means for each one of those eigenvalues, each one of them can give me at least 1 linearly independent eigenvector. There has to be a non-zero vector that makes that happen. So right now, I have at least 3 eigenvectors, right? 3 linearly independent eigenvectors, which is almost enough, but not quite. All right, what else do they tell us? Furthermore, suppose the eigenspace for lambda equals 3 is 2-dimensional. So the dimension of the eigenspace with 3 is 2-dimensional. Well, that implies that its eigenspace is the span of 2 vectors. Right? So do we have enough information to determine if A is diagonalizable? Look what I have on the board here. We need 4 linearly independent eigenvectors. We're now told that for this eigenvalue, it has dimension 2. Therefore, its eigenspace is the span of 2 vectors. So I have 2 vectors from this space. There's 2. For this eigenspace, I get at least 1, because it has to give me at least 1 eigenvector, 1 non-zero vector. So that's 3. And then this space must also have at least 1 eigenvector, right? So I have a total of 4 linearly independent eigenvectors. Even though I don't know where they are, even though I don't know what they are or how to find them, this question has given me just enough information to know that this matrix is, in fact, diagonalizable. All right? So A is diagonalizable. And that is the final answer for our last participation question in this class. A is diagonalizable. All right? So that's all for today. If you have other questions, please, by all means, do email me. Tomorrow evening, instead of having an office hour, we're going to have our review session on Zoom. So what we'll do is that Zoom link for the office hour, while that's usually the office hour link, we're just going to use that same link for the review session. And I'll post details about that tomorrow. And then we'll have our final exam on Wednesday. It'll be the same kind of thing we did for the midterm. It will open on Wednesday, right? So as soon as Wednesday starts, that's right after midnight on Tuesday night. You can start the final whenever you want. But again, like the midterm, you want to be careful. Once you start, the timer will start going down. You will only have 2.5 hours to complete the final and 2.5 hours to submit your final work. So you want to make sure you get that in. All right. Now, in terms of the length, the final exam, of course, you only have 2.5 hours, right? So I can't give you too many questions. It will be a little bit longer than midterm, since that was an hour and a half. So questions. If you finish early, upload it to the assignment and you're done. You don't have to use the whole time unless you want to. But otherwise, that's going to be the idea. It's going to be free response, just like the midterm. I'll also give partial credit. And there will also be a bonus question at the end. So it is possible to get over 100 on the final exam. So if you're some student who's possibly needing some points, that can be a way to get some points. If you just really, if you do really well on the final, that can be a huge boost to your grade, right? Okay, that's all for today. Best of luck, and I will see you tomorrow.